Okay, welcome to another episode of Bitcoin class with Dr. Craig Wright. My name is Xiaohui Liu. I'm a student of Bitcoin, and in this class, we're trying to teach Bitcoin from a theory to a practice. So today, we are going to cover some cryptographic topics and also what can we do about metrics. So what are we going to learn today?
All right, so I'm going to cover off some other areas for you to start looking at and building and start considering in making simplified sort of applications that we can build upon. Now, there are two areas I want to cover. One is actually fairly much natively there, but we can build upon it in the same way as we have with Python and even C. That is the actual native stack.
Okay.
So we have push operations, pop operations, etc. Now, using the stack and the alt stack and being able to save our data or get rid of it or whatever else, we can actually start doing all of the queuing functions that we have that we work on in Python.
Queuing functions, what do you mean?
So if we wanted to do calculations on queues, like
queues, okay.
bus stop, those sort of problems, which are another problem that people want to solve.
Okay. So what are the potential application for this kind of like a queuing theory or related?
Well, calculations in how many people can get through sort of different queued areas, boats, logistics, etc. So imagine that we have one big long tunnel and there's a boat in the way. Nothing.
Okay, yeah.
But if we have two, how many can go through at a time? All those sort of fun things. So if we have 4 queues and one line that goes into them versus 4 lines, what if we have 4 drivers? How quickly can we get goods out? Will we get our pizzas on time? How do we could calculate how many people we need to put on for the night, if we get more orders, etc.
I see. But how is it?
These are all outsourced problems that we can give out to people.
Okay. Yeah, I think when I took the queuing theory, I think part of my graduate education is mostly talking about different arrival process and different and like a Poisson or exponential waiting time, and then you can compute something like a average waiting time or serve time. How is this related to Bitcoin here?
Again, we can put calculations that people can solve. We can have things based on if a particular input queue is full, if information would appear that it's going to be full.
Okay.
So if we have multiple inputs, we have people able to sign up on something. We could have, remember, we can have multiple inputs and fire off a transaction every number of items or goods or whatever else. Excuse me. That would allow us to have something like, instead of Lighthouse, we could have a time-based system. And every 10 minutes, we fire off the transaction, every 5 minutes, for instance. So we say that if there's too many, then we might need to set up another one.
Okay. So when you say input, is it the input of the queue or is the input of a transaction?
A bit of both, really, because the input of the transaction can go into the queue.
Okay. So what is so the queue, right? When we talk about queue, usually when we say what's arriving and also who's serving, is it arriving is the transactions and what's serving is the Bitcoin mining network? Or?
A bit of no, forget the mining network. That's irrelevant for transactions. It's when it gets paid. So we could have an end lock time transaction as a fail safe for if we don't get enough, we just every whatever period of time put in process. But otherwise, if we get too many, we can process it early. Otherwise, we build up a certain wait time as we're getting orders, and every now and again we do our order. So the queue could be we process sending out purchase orders when we have enough demand.
Okay.
So so if you think about lighthouse transactions, they allow you to have inputs that if I get to a certain amount, the transaction becomes valid.
Yes.
So simultaneously, I could have a series of transactions where if I get a certain number of orders or a certain number of value or whatever else in a time period, now I fire off my series of transactions that maybe buy extra goods, increase the amount of factory time, increase the AWS storage sort of costs, etc.
I see. So, okay, so here, this transaction, they can be independent or they can be somehow chained? Or...
Yes, both.
Okay.
But remember, a single transaction can have a number of inputs, and we can, all this, the transaction's not valid. We can have an input transaction that fires after a certain time.
Okay.
So my transaction becomes valid for this other transaction and allows you to put the whole lot together if end lock time has passed.
Okay.
So imagine at time 0 and time 100. At time 100, end lock time kicks in, and a transaction that I've signed can complete whatever in the other transaction. If there's more paid, I don't care because it goes back to me anyway.
I see.
On the other hand, if users putting whatever else in at time 1, at time 2, at time 5, at time 10, I can now build a series of inputs. And if they're too large, too many required items, whatever else, I could, for instance, have that processed and send off different transactions.
I see. Okay. Yeah, I think this kind of reminds me that in the first class, we talk about this transaction graph, kind of like holding this offline. Somehow reminds me of that. So, so here, I can see the arrival process. You can think of the just transactions, Bitcoin transactions to keep arriving because maybe triggered by some external events like a customer coming, buy a coffee or buy some, I don't know, apples or whatever. And the one who are serving it may not be a Bitcoin. It can be, as you mentioned, right? AWS, we try to scale up. So that is that okay? Yeah.
So remember, we're just talking about data. So everyone thinks the only thing that matters is the amount of Bitcoin or whatever else, but it can be anything that we want effectively in Bitcoin. We can put things that process and give us images or whatever else. Now, we can, how much do you know about things like compression algorithms?
A little bit, lossless.
Now, what you'll remember is that these are matrix operations.
Okay.
So if you think that we have an image or something like that, we want to not decompress it, but expand it out.
Kind of like a transform it some way, or?
Yeah, so we can make we can have a compressed image that loses, well, integrity, unless we have another matrices.
Okay, so that matrix is almost like a kind of like a recovery key kind of thing. You only have to.
Well, not even recovery key, but you know, in machine learning, how you do decomposition exercises where you break things into sort of matrices that you multiply by each other, USD or SUV type methodologies. Yes, no.
Not much, but I only understand the matrix multiplication part of things, different transformation.
Let me remind myself. Okay, so what we can do there is actually have an image that loses some of the quality.
Okay.
Effectively, we decompose the matrix into only partial information and another matrices that we can effectively use to rebuild that, decompress it. So
almost like a shared secret key?
Not really a shared secret. It's actually a value associated with the matrix itself.
Okay. So once we have different, okay. Once we have this kind of a two matrix, what can be done?
Yep.
I mean, what kind of a once now we have the different two matrices? What is next? You mean you can, for example, you may have some image you want to sell and
well, yes, you decompose the image and you get rid of basically it breaks down and gives you a lesser version of it. So it's used in machine learning so that you could not have as much information to process, otherwise machines clog up, etc., etc. If you look at the machine learning stuff for facial recognition and everything like that, what they do is they take the main features of the image, and it's not as crisp or clear or anything like this.
Like a blurred version, but you can.
Yeah. So it's not your 4K version or anything like that. Now, that would allow people to do things such as viewing and accessing and having a look at a picture, but they can't expand it without extra information.
Yes. Okay. Yeah, it reminds me somebody has trying on this Bitcoin or some other platform. They try to sell you the full image of some, I don't know, beautiful mountain or something, but you don't know what they don't want to show you at the front.
Yeah,
so
I mean, or
kind of like a
it could
blurred
just
version.
be small. I mean, it could be a 300 by 200. Looks good and small, but you try and expand it out and it looks horrible.
Okay.
And it's all pixelated, whatever else. So that would allow you to then create things where people could look at it and the information stored, and then you can sell them something to expand it out and access.
I see. Okay. Yeah, I could imagine this can be useful for some kind of like that's called a replica. I think they're trying to do kind of an Instagram type of thing on using Bitcoin.
Yeah.
So that could be something.
Or you could have people who pay versus people who don't pay and all that sort of fun stuff.
Okay. Matrix. Okay. Yeah, there's almost like buying almost like an access token, but this token is within a matrix. Okay.
So we could send them something that they multiply with their transaction, and voila, the information is now out there and clear.
Yeah, I could imagine some industry that may not be, some other industry may be using this, I could imagine.
Well, I mean, the whole silly thing with like NFTs, what we could do is have something that's far better. Like you could have the public version of an image that has no real integrity or anything, but you own a private version and you can rent it out.
Okay, sounds
so people want to use your file and publish it, then there's a record of the use, record of the payment, etc.
I see. So it's almost in the domain of, at least in the domain of digital record DRM system. You can enforce some kind of like a copyright. Okay.
Yeah. All sorts of other things like that. Now, we should also try and build up some of the other functions. So once we have matrices in there, we can start building things like mean squared error.
Okay.
Mean absolute error, and some of the other statistical bits of information. That will allow us to not only have things that are perfect, so to speak, i.e. it's exactly this, but we can look at alternatives. That is where it's between values or it's more likely. So someone does X and they can provide a value that is 99% likely to get there, and we can pay for that too.
I see. Yeah, I could see a lot of use cases for this kind of almost like a selling access. So before you mentioned a little bit of the whole so-called Hill cipher. Are we going to cover some part of that today, or?
We can. So effectively what we're doing there is, once again, a multiplication mod value. So let's, I got a little
whiteboard. Okay.
Bring up.
Okay. 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 I think, yeah. Lower it a little bit, maybe lower a little bit. Okay, that's good.
All right. So what we're basically doing is we would set something up.
Can you lower a little bit? I think I can see almost the top.
I just have to move it to the right, and then I'll.
Okay.
Okay, so
I can see the top ABC. Okay. Okay. Yeah, that's much better. Okay, we'll talk about the Hill cipher.
Now, the thing you get is then by some value and that's going to give you another matrix, and effectively we can mod 26 that and get our values. Now, with all of this, what we can do in encrypting and decrypting this is, of course, if we have A by A to the -1 equals the identity matrix.
Yes.
So whenever we do a calculation, we can do the opposite. So if we have here A and X, so AX equals Y, then AX A minus equals Y A minus equals X.
Yes. Yeah. Just decryption.
Yeah. So what we do is we multiply values out. It's an easy, of course, because through
Okay.
You could run through, students do this sort of 3x3 matrix all the time. On the other hand, if I wanted to say have a 256 by 256 by 256.
Okay.
matrix,
Probably you don't want to do manually.
No. I mean, it's theoretically possible, but it'll take you a hell of a long time.
Yes.
I mean, I'd be handing it off to a computer if I was having to do this. Now, when we're doing that, we can use this as input filters, etc. So Old Hill there, although it's not the most secure algorithm, provides just a little methodology for munging things up.
Okay. Yeah.
So people say about wanting to encrypt values and things like this. Now, it's also possible to calculate alternatives.
What is alternative here?
We can have this match to address functions, for instance.
Okay. Address function.
Well, I mean, in the simplest way, if this was 256 long, 0, 1, 0, 1, 0, 1, etc., then we can basically come up with our matrix here that ends up a 256-bit number.
Okay. So we kind of treat X and Y as like a Bitcoin address. Is that what you're implying?
Yeah, we can actually make this into an address function. Yes. And we can say if we match, then that's valid. And there are sometimes more than one possible outcome depending on how we allow input filtering into this.
Okay.
So that means we can start having calculable outcomes for effectively different key values. Also, mask values. So remember we said about masking values with XOR, etc.
That's another way to mask it. You're using a matrix.
Yeah. So part of your calculation could be in all of this. So say we want you to calculate the mean squared error of a very large block.
Okay.
Like mean square. So if you're doing something like a mean square error calculation, generally it's done by, I mean, there are ways without matrices, but matrices are probably the simplest and the fastest. So you put it out there and allow people to do the calculation and take the value, and it can be done in such a way that the information can be private.
Okay.
But both parties know.
Okay. So that's yeah, this matrix. I'm looking at this, and it's inverse. It's almost yeah, it's a shared secret between probably the sender and the receiver.
Effectively, yes. For putting information inside some of these calculations.
Okay. Yeah,
now,
it's almost okay. Go ahead.
So the other bit is, if you remember, the inverse can be taken on either side to remove the effect of the matrice.
Yes.
So what we can do is we can multiply a matrix and then continue doing operations. So we can now have, if we do the right sort of matrix and inverse, have things where we can start doing homomorphic principles, in that the two parties may share a matrix mask beforehand. This could apply to the output address. So you can't cheat. So there's no, I'm going to put the wrong value in or anything like this, because it will still go to the value. And now I require that you solve this problem that involves a matrix, that I will now do a simple operation when you return the answer by applying the inverse. And I know that, you know that, but the average person on the internet won't know that. So although the information is public and the calculation is provably done, you still won't have the answer.
Okay, so that's the part I think I'm not following. So I was thinking about when you have the, for example, the encryption matrix, say A, and you lock up something inside the UTXO, and then you are going to unlock it using the decryption.
Yep.
But then once you put in the unlocking script, wouldn't that be also the inverse of A already be public? That exposed kind of a secret key?
No, because you can do calculations that require it without actually having to have all the values in there.
Okay, almost like a, I don't know, like a homomorphic encryption. You can do calculation on the encrypted values.
So we can also exchange information privately offline. So okay. I could take your key and mix it up and know that to get paid, you have to apply this this value.
Okay.
But that value also applies to the calculation you're doing. So when the answer is there and you make your payment, I know that you haven't cheated.
And also somehow the secret we share between each other may not end up on chain.
Exactly. That's where people go wrong. Okay. Not everything ends up on chain.
Okay. So, okay. So in this example you just mentioned, which part of it is down in on chain in script, which is kind of off chain when we are only doing in private?
It will vary, but if we're doing, say we wanted to do a system of linear equations, nice complex one, and we're putting a reward out there for someone who can solve this.
Yeah, it will be like for some students. Students,
not the simple student ones, but really complex ones for optimization problems or something like this. Now, we're not doing the 3x3 matrices that students get or anything. We're doing a 108 by 108 matrix.
Okay, yes, that would be probably, I would like to pay somebody to do this, because I think, again, this kind of like a fit in the model is difficult to solve, but it's much easier to just verify, because once you give me the answers, I can just plug in to see if that's all equal. But on the other hand, it may be, it's similar to like a matrix operation. Sometimes some of them is pretty computational intensive. Is that why people may try to? Is that how also fit into the paradigm of just the
but doing an inverse multiplication of a matrix, it's I mean, on 108 by 108 one, we wouldn't want to do it by hand, but a computer will do that really quickly. So if we know that the invoice is the inverse is a particular value, we plug it in, and that works. Now, remember, we could also multiply that by other sort of values, such as to get a key by some other value that we put in the script. So where I was saying, like the equivalent of hill there, so
that's good.
We have our sort of calculation, but we can say that you need to multiply this by another value, and then you need to put something else in here that is derived, because of course by the inverse will get you the original. So ax equals y, so ax a to the -1 equals y equals x. So if we want to be able to calculate that and that, we can do the same.
Meaning?
So we can take this and that and work out the opposite. So we can work out x and we can work out y. And just as I was saying here, y equals x, then we can also get back the x value, which may not be publicly visible.
Okay. Let's say, what would be one example of using this combined within Bitcoin? What is, again, coming back to the, you may want to sell some image?
You've now got matrix problems. So we want someone to solve something, and we want this value So what we're going to do is have them have this Y value that they get paid to.
Okay. So only if
But,
they find the right matrix A, it will be
well,
transformed.
no, we could actually use that as a key to undo all of this.
Okay.
So, I mean, they have to give us an answer, and they can do that in a variety of ways.
And
That
the answer here
now,
is Y here. The answer is Y
well,
or is X?
no, I'm just giving a few different things. So imagine that Y is a payment key that they get paid to.
Okay.
And we have something where we calculate that.
Okay.
And they have to be able to put in information to get that.
The information is encoded in A or is X? Kind of both.
It could be a bit of both. So it could be a function of two of these that is not offline. So, but what we can have, because we have that, and we can have a different calculation that also uses the inverse. So they need this to calculate out, and we can calculate using the inverse that they need to send to this address. Okay, but they don't send to that. They have to get something that calculates with this and that. And then they also have to make some other value. And whatever they've calculated B to be can multiply by that, and they could.
I think, yeah. Can you raise it a little bit? I think it's just outside of the camera, just a little bit. Okay, that's very good. Thank you. B. Okay. What is B here?
It could be anything. Just anything. Okay. I mean, there's no particular. There's just it's arbitrary. I mean, any viable matrices that we can add, subtract, multiply, do operations on, etc.
Okay. So I think one example I could think is go back to the previous example we talked about is you are kind of trying to sell like a full image, but you don't want to expose it fully at the beginning.
Right.
You may want to do something using this.
So yes, we could have all of the information sitting out there, and effectively an image can be put into a matrix, and then if you want to have the rest of it, the decomposition values to expand this back out into a full matrix, then you pay the money and you get sent that value. And the only way to make sure that works is, for instance, having the information incorporated in the payment.
Okay. So somehow you need to find the inverse of A, which is a decryption key, allows you to recover the full image. But somehow you have to get that.
I call it that.
Yeah, it's
decompression.
Decompression. Okay. So for that to happen, you need to pay. That's it. You pay to some like the author's address.
So by tomorrow, what I'll do is I'm going to send you some homework.
Okay.
In some of the machine learning stuff and image decomposition. So all of this is basically just statistics. We like to call it machine learning, but machines are just probabilistic engines that take values and pretend that they're smart.
It's like the internet meme on Twitter, like whenever people say machine learning, AI, you just take off the cover. It's always like a probabilistic inference over there.
Yes, exactly. So yeah, all of the other calculations that we can do using a matrix, we can extend out in the same way. So that allows us to calculate individual numbers, ranges of numbers. We can still do mod functions on them. All sorts of fun and funky things.
Yeah, I think the part I get is that once you can do some basic matrix operation like a multiplication or inverse, you can do all sorts of like even more advanced. Maybe you can do a Gaussian elimination or calculating whatever determinant. But what I'm missing so far is what kind of is it trying to port what other languages have been doing, like say R, Python with
in part, yes.
In script, or what is
yes, because we want to actually be able to include part of it. We want people to do most of the calculations, but then be able to validate what they've been doing in script.
Okay, validate. Okay. Again, we are always coming back to this theme. I feel is that you only have to verify. It's similar for the equations. Like you have a list of equations. Maybe it's hard to solve, but somehow you need to convert it. Just need to check. So let's make the script much simpler, and you don't have to rerun.
Yep.
Okay. So similar things here. Maybe we want to look at some of what other languages like R or Python. They have been doing a lot of matrix or statistical things. We want to.
The reason being, effectively, what happens is matching values, perceptrons, etc. So let me try and find something for you.
Okay.
So you then let's see what we've got here. So here's one. This is probably not the best, but it's just a quick thing. Let me pop that in your chat and let you have a look as we're talking.
Okay.
All right. So.
Okay, I'm looking at it right now. Matrix decomposition for machine learning. Okay, application.
Yeah. So what we do is we take the main information out of files. So in machine learning, you're trying to find the main features that the image will sort of appear the same on. You lose resolution, but that's not always going to matter so much. So if you look at the SVD low rank images in there, you'll see that some of these look fairly much the same.
Yes.
They're not too different. They basically pixelate things, and they have a visualization of the matrix factorization. You don't need to do the matrix factorization in script, but you could put the value in to effectively create something that gets you the information that you originally had back.
Okay.
So in the images there, for instance, you have a smaller image that when multiplied by another value gets you the original image back.
I see. Okay.
So you see how you've taken like in the example I've given here, there's D factors, movies, whatever else. SVD allows us to take like a couple columns of matrices and save those values. And then all of the information is contained between those two matrices. But if we only have one of them, then you have lost information.
I see.
But it can be enough, for instance, to get the basics in a pixelated format of the image. So if someone wants to buy a picture, they get the low quality one. And now you pay extra money and we give you the thing that you multiply it by. Okay.
You get the more fidelity one.
Yes.
Okay.
So imagine you want to buy high definition versus SD. You pay a different amount, you get a different key.
Yeah, that would be have some real application out there. I would
And
some of them
it saves money on how you save it as well. So you
because
can put the compressed form online.
okay.
And then when people pay you for it, they get the uncompressed form.
So the benefit of using this kind of approach, incorporating Bitcoin versus just hosting on some centralized server like YouTube, is the transaction cost or Netflix?
Well, it's a provable transaction for a start. You now have the image you want to buy. There's no one can go, this is something different.
Okay.
You know that the person owns it. You can have proof of ownership. If someone did own something like the National Basketball League are selling these silly NFTs,
Okay.
instead of that, they can actually sell something that has value. You can have the rights and you can resell it, and you can say, you get access for a week for this, you get access to this, but only for this purpose. All of that can be built in.
Yeah, it's more programmable, it seems to be.
Exactly. And now, rather than saying it's on YouTube or whatever else, it could actually be linked to applications, and people could pay rights to use the images.
I see. Yeah, it's always, I think it's enforced copyright on the internet is always a big issue, because it's just, you can always digital, so it's always you can always copy it, and it's hard to track. I think it might be put on chain. I think at least you may want. It's just easier to trace it.
Yeah. So now all the access relates to the low rank image, and you can extend that back out to the full matricity by doing a calculation.
I see. Yeah, it's almost like you have kind of almost like compressive with some metrics. But when you want to decompress, you need to find, I don't know, some other metrics. Yeah.
So you've got some homework on SVD is singular value decomposition, and the other is non-negative matrix factorization. That using that, we could take, it doesn't need to be images either. It can be other things as well. So we can take our original data and basically make it into a series of like vectors or other like lower columned matrices, and lose information, but be able to rebuild everything if we need to. And this can apply to other data as well. So if you want, for instance, climate data, you could pay for something that is approximate.
Okay, like a low quality.
And you can pay more for high quality. Imagine medical data. Someone can provably show this is my survey data. And then when people want access to the better quality stuff, they pay more.
Yeah, I could imagine this. Instead of just have two tiers, like a low quality, high, the regional, you may even have a different hierarchy of quality. Just the more you pay
can be done in different amounts.
Okay, so instead of two metrics, you may even decompose it more. I haven't studied that, but it seems that's what you are inferring.
I am. And you lose more information, and eventually you won't even know what the image is. So you don't want to go too far, but you get it's a balance. So you maybe have a totally cruddy little image, then standard definition, then high definition, then movie quality.
Okay. Yeah, I think I think people are already familiar with this type of quality. Like when you stream on YouTube, you can. It's always depending on bandwidth. Even they can auto select which kind of resolution you can have.
Exactly, and the sort of recalculation of matrices can actually sort of vary depending on what you pay, etc.
Yeah, that's something very concrete. I can work on. Probably construct some simple examples.
Good.
Yeah.
So I think that's probably the things to get you started on first.
Okay. Yeah. That's.
Start looking at. Then we can do things like principal component analysis, pull out extra information, eigenvector calculations, other fun things. But let's first of all work out how we can decompose the information and maybe embed a image at low quality that someone could pay and get high quality.
Okay. Yeah. That's. I think it's a funny thing is I always talk about this kind of latest technology. It's some gray area, I would say. Don't name the industry, but they always seems the pioneer to use it.
Yeah, I don't actually know if this is really the reason people use this, except I generally go and redeploy things all the time. As I said, in machine learning, this is used to reduce the size of data sets because you can get most of the information and sometimes it's much more effective. So if you have a really large data set, it could take you years to run. So you extract all of the main information and you can run it in real time. And it's accurate enough.
Yeah, I could imagine. It's like you're trying to see if there's a dog inside something like a picture. You probably don't care about the background. You can pretty much blur them out. You can still get the right answer, but you don't have
features of it being dogness. So you want the main dogness features. Does it have this sort of shape? Does it have 4 legs? Does it? Yeah.
I see. Okay. Yeah.
The same thing can happen in what we're doing, but we can take it for a different purpose. We can use it for basically making reduced quality out of the high quality stuff that can be recoverable at different levels depending on what you pay.
Yeah, I could see this not only applies to image, but just any other type of data where you can have different quality, and probably you want to pay premium.
Yeah, financial data, for instance, can be put through such a filter as well. And you can have something free and provable, but if you want to drill down and get the sort of to the nanosecond stuff, as people do, you pay more.
Yeah, makes a lot of sense, I think, in this case.
All right, so I think that's probably a good thing to get you started on. I'll send you some more information on SVD, etc. in the morning. And have a look at that site I sent you for now anyway.
Okay, yeah.
I'll send you the actual, what you need to do. And we can start this in script.
Okay, yeah, sounds a lot of exciting things we can build upon this. Cool. I think
for all these people who thought that you couldn't do anything in Bitcoin script.
Yeah, you can do only tokens. So far. Let's see.
Well, we're doing machine learning algorithms at the moment, so that's what these are.
Yeah, that's already a big category. Yeah, AI and next stuff. Okay, thank you very much, and I will see you next week.
Will do.
Okay, take care.
Alrighty.
Okay.